Jai Hind to all. My name is Dhanshri Parihar, Assistant Professor, Department of Computer Science and Engineering, Akgec Garg, Engineering College. Today, I am delivering the lecture on the subject Computer Organization and Architecture, and the topic is Processor Organization Schemes. So, before proceeding for this particular lecture, we have the contents of this presentation. It includes the introduction regarding the organization schemes, the accumulator-based organization scheme for processor, the journal register-based organization scheme, and the stack organization scheme. Now let us have a look at what is a processor organization scheme is. In journal, both the processor are organized into three ways. The very first phase is the single register, that is the accumulator-based organization scheme. As per the Morris Mano author, the accumulator size is 16-bit. So we are processing 16-bit of data in an accumulator, and it is a kind of a special purpose register which is used to store our intermediate results of the arithmetic operations or the logical operations. So on the basis of this organization scheme, the computer is very simple and the accumulator is a general purpose register for that, storing that intermediate results in this scheme. Along with accumulator, we are using the program counter and the instruction register to store the instruction and to store the address of the next instruction to be executed. The next type of scheme is journal register organization scheme. In this scheme, the modern computer processor basically use this scheme and the register can be used. Here, the multiple general purpose register are used to perform the arithmetic operation or the logical operations. And the third organization scheme is the stack-based organization scheme. In this, the register or either your RAM will be organized in the form of a stack like LIFO format. So let us have a look at all these three schemes, how we can use these schemes to organize our processor. So the very first scheme is single accumulator-based organization scheme. In this organization scheme, as we can see in this diagram, we're having a common bus system over here that will be used to interconnect all these blocks. Like memory is there, okay, the program counter is there. What is program counter? It is an address container. Address container of what? Address container of the instruction itself, which is going to be executed next. So the address container of instruction, which is going to be executed next in your instruction cycle. Executing next. So that address will be available in our program count. So before executing an instruction, the CPU will issue that address. It will be issued by the CPU only. That physical address will be given to this program for this program counter, and that address will be fetched into the memory. Memory are having the labels of the instructions. As we all know that the memory is container of the data as well as instruction itself. So it will be composed of data and the instructions. And whenever the PC will point towards this memory, it will pointing toward the address of the next instruction to be executed in the instruction cycle. So after getting that address and that instruction need to be fetched into our instruction register through our common bus system. So that 16-bit of instruction, in case of this author Morris Mano, has suggested a 16-bit processor for this particular curriculum. So 16-bit instruction is there in residing in the memory, and after getting the address, that particular instruction is being fetched from the memory to our instruction register. Now what is the instruction register? The register, a special purpose register that will be holding the instruction which is being fetched from the memory to it. And after that, that instruction is being decoded, and that decodation of this instruction register will result in the outcome. What kind of operation needs to be performed? Either it is a register reference instruction, memory reference instruction, or input-output reference instruction, from where we will get the destination where that instruction need to be performed on what kind of operands. And after that, the result, half of the result or one of the operand. Suppose we have to perform this operation A plus B. In this case, we can store the first operand in the accumulator, Meanwhile, the B is inserted from the memory into our instruction register. We are getting the instruction for getting that particular operand from the memory. Meanwhile, we can store the value of A in the accumulator. Now, after that value is being stored in accumulator, this B will also be passed to the ALU, maybe either through some other special purpose register, through data register, or maybe through some other kind of general purpose register. One is held by accumulator and one operand is held by some another register, or maybe that will be reside in your memory. The ALU will perform the arithmetic and logical operation, and the result of that operation will be floated from the common base system and stored in the memory. And the same cycle is being followed until that set of instructions will get executed. And one by one instructions are their address is being stored in the program counter. Each time the program counter is incremented by 1. So such kind of scheme in which the single accumulator is used to perform the arithmetic operation like addition, multiplication, subtraction, and the logical operation is known as our single accumulator based organization scheme. Although this scheme is very beneficiary, as it is very simple in nature, but the problem with this scheme is that if I want to multiple operands to perform the operation on multiple operands, so the system is not that much capable of performing the multiple, we can say multiple complex operations, arithmetic operations. So that's why the second scheme known as the journal register organization scheme is being introduced. Now in this scheme, instead of using a single accumulator along with some another register, here we are using this journal purpose register. The journal purpose means these registers can be basically used for storing multiple type of data in it. More than one value if we want to store, so we can use all these registers, and we want to store on the multiple destination. That's why we are using. So here this R1, R2, R3, 4, 5 till your 7, these all are our journal purpose register. As we can look at this scheme, we have two multiplexer over here. So what are multiplexer? Multiplexer is a kind of a component that will take 2 raised power p inputs and 1 output. So we are having 2 raised power p inputs and 1 output in a mux. 2 raised power p means in the power of 2s. And what is the p? P is a special kind of input, we can say selection lines, which will control the dependency of which input out of the multiple input is being selected by the multiplexer. As we can say in this diagram, we are having two multiplexer, each of ratio 8:1. Here, the value of P is 3. As we can say, the 8:1, it is 2 raised power 3:1. So, P is equals to 3. So, we are having 3 selection line for these two multiplexer, 3 for each. It is shown over here, selection A and selection B. Okay, what is the role of these selection lines? Actually, these selection lines are used to select which out of these inputs, either 0, 1, 2, 3, 4, 5, 6, 7. Out of these 8 inputs, which is going to be selected here. That will depend upon the code inserted from these 3 selection lines. For example, here it is code is 0, 0, 0. It means the position number 0 input will be selected out of the 7, and we will only get the position 0 result in its outcome. So this type of component is used to make choices among multiple inputs and to give the single output after segregating on the basis of that selection format. Further, we can see that ALU is connected with the two multiplexer to perform arithmetic and logical operation. As we can see in this particular operation code diagram, here we are having 6, 7, 8, 9, 10, 11 arithmetic operations, which includes transferring of a value, incrementing a, adding the contents a and b, means two operand addition, subtraction, decrementation of an operand, ANDing operation, ORing operation, XORing of, and the complementing of the single value, along with the two shift operation, shift right operation and shift left operation. So we have 11 arithmetic and logical operation which is being supported by our arithmetic and logical unit. So here in the lower diagram, the example of such kind of operation is being given, and we can have a look on the control word. What is a control word later on? Let's first have a look on this diagram As I show you that P selection lines we will use, and we have this multiplexer. Now here, this why we have used two multiplexer in order to make selection among two operands. So the operands will lie in this general purpose register, any one of them or all of them. And out of these 7 register, which operand I am going to select, that will be decided by the multiplexer 1 and the multiplexer 2. And when we get two operands, suppose here we are having A or B operand floating through A bus and B bus, we will be performing some ALU operation on two operands only. So this setup is for performing the operation on two operands only. Okay. And whatever the result we will get, that result, the result of addition, subtraction, multiplication on a two operand will be stored back to these registers. And how that selection is made for selecting in which particular register that output is going to be restored will be based on another device known as decoder. Now, what is a decoder? Decoder is a component which is having 2 raised power n inputs and m outputs, we can say. Sorry, n inputs and 2 raised power n outputs. That is having n inputs and 2 raised power n output. That is your decoder. As we can see over here, we are having the value of n equals to 3. So 3 inputs is equals to 2 raised power 3 output, that is 8. So it is a 3 into 8 decoder, which will be having 3 kind of input in it, like the selection line. And the selection line will decide out of these 7 registers, 1, 2, 3, 4, 5, 6, 7, which register is going to be selected. Suppose here we have a code 001. So 001 is for R1. We can say it is at position number 1. So R1 will be selected as a destination register to store the output value. So this is a kind of, we can say, and this load line actually indicating out of which, out of these 7, which of the register is going to load with that output that which we are obtaining from your ALU. Okay, load signal is the indication of making that register active to obtain the output. So in this way, this particular journal register organization is used. Here we are having one more input, that is from the external source, we can say CPU at 00 location. So we are having only 7 register over here. Now have a look at how we can perform a simple operation on this multiplexer, on this journal register organization using this multiplexer and ALU. So let us have a look at the example. Suppose we have to perform the addition of 2 operand which are residing in register R2 and in register R3, and the result of this addition is being stored in register R1. So performing this operation, we are putting this R2 in our multiplexer A and R3 in multiplexer B, indicating that the 2 operands are being selected by mux A or mux B on the basis of their selection line set according to their position. So we need a selection code for R2 in multiplexer A and for R3 in multiplexer B. After then, the operation which need to be selected in ALU is your addition operation. Here, what 5-bit code is used for selecting the addition operation? We can see over here, to add 2 operands, the code must be 00010. That is the code which is being inserted into ALU, and then the ALU start adding the 2 operands. That is the code for addition operation. Similarly, we are having the rest 10 codes for performing other ALU operation as shown in this table. And the decoder, what will be the destination register? That is R1. So that R1 is an output register. Here the selection D line will must focus on the code of R1. So let us have a look how this operation is being performed. How we can do this. So for doing so, the CPU will issue a control word of 14 bits. As we can see over here, control word. So control word is generally a kind of an instruction which is a 14-bit of instruction, we can say kind of instruction which is containing all the information about what task is going to be performed in this organization scheme. Right now, as we know that we have to perform the addition of R1, R2 and R3 and to store the result in R1. So for doing so, what value we need at selection A line and what value we need at selection B line? What at D? we need the value of R2 for getting it being selected by multiplexer A. So as we can say that R2, it is having number 2, so code for 2 is 010. So how we can make its control word? Like this. If I'm saying this is selection A line, so what code I can insert in this? This is 010. What will be at selection B line? This is the formation how this control word is used. The first 3 bits are reserved for selection A line, second 3 bits are reserved for selection B line, next 3 lines are reserved for selection D line, and next 5 bits are reserved for operation code being performed by ALU. So here, for making this 3-bit code, how we can make it? We will have a look at this first register that will be holding our first operand A, we can say. So what will be the code for 2? Binary 2, that is 010. And for B, what will be the code? It is for B, we need R3 to be inserted in B. So what will be the code for R3? That is 011. And what about this? The selection D lines. Selection D line, the destination register is R1. The code for 1, that is 001. And what about the last? That is the operation code lines. We need a 5-bit of code to select the operation. So operation is addition operation, and for performing addition operation, as I told you earlier, the 5-bit code is 00010. So I can insert over here 00010. So this is we can say this is selection D line, and this is your operation code OPR for ALU. So this is a 14-bit control word which is being issued by your CPU in a form of binary numbers, indicating what operation this need to be performed, how this organization is done. So this control word is inserted, and by fetching this control word, we will come to know that first of all, our register R2 is being selected. As I told you that the mux will be having what code in selection A lines? In selection A lines, it will be having 010. So here we are having 010. Now this is 0 position 1, 2, 3, 4, 5, 6, 7. 010 is for this location number 2. So this line is being selected, this one. Okay. Other will be rejected by the multiplexer. In output, we are getting your R2 here over here in A bus. Okay. Similarly, for this mux, as we know that the second operand will lie in R3, and the code for R3, as mentioned over here, is 011. So here we have 011 selection line, and how we can get selected? 1, 2, 3, 4, 5, 6, 7. This 3 position is being selected, and here this line is being selected for R3. And we will obtain the operand which is stored in R3 over there in this bus. So output of multiplexer is the operand stored in R3 and R. Now here in ALU, we will performing R2 plus R3 operation. Right now the destination is not known. That is known in the instruction itself. So R2 and R3, the ALU operation, the arithmetic addition will be performed. For addition, we have code 00010, which will be insert over here. 00010. And now the addition will be performed. And result will come over here, whatever will the result of addition of R2 and R3. But how we can come to know where it is going to be stored? So in this instruction, we need to store the result of this 2 addition operation of 2 operands residing in R2 and R3 in R1. So destination register, as we have selection D lines code 001. Here we will insert 001 from the control word. And what we will be obtaining? We will be obtaining destination register to be R1. So here, when it will insert, this load line will become high, and which of the this output will automatically go to R1 and rejecting all other 6 register in this die. So this is the way how we can perform an addition. Similarly, we can perform subtraction, multiplication, increment, decrement operation in your ALU. And the selection source is our multiplexer, and the destination decider is your decoder. So this kind of organization with multi-purpose, we can say register which are known as journal purpose register is known as journal register organization scheme. So it is a second kind of scheme. Here we can say that if the number of operation or operand become high, again we need a very big hardware to perform that operation. So the third scheme will be invented, which is known as stack organization scheme. In this, a very minimal hardware is being used, okay, what we are going to use? We are going to use either register, we are organizing a register as your stack, or either we are going to organize memory as a stack. Now, what is stack? A stack is a data structure that will be in LIFO format. LIFO means last in, first out format. So, whatever we are putting in a register, it will be organized as a stack. Okay. And why it is very useful? Because this kind of organization is useful when we are dealing with subroutine and calls. So that this kind of organization scheme is very beneficial when one instruction is going to be jump into next, skipping 4 or 5 instruction or thousands of instruction and need to come back to that particular instruction again to resume the execution from the previously executed instruction. For that kind of, we can say, instruction set, we can use this stack organization scheme. So here, if we have a look on the first scheme, that is a register stack organization scheme. In this scheme, this is a common, we can say, register. This will be of 64-bit and it is organized like a stack. So 64-bit of register is there and it will be holding certain data operands A, B, C along with their addresses from 0 to 63. Here DR is your data register, which is used to transfer the data, either for fetching data from data register to the stack, that is journal register, or either obtaining the data and restoring in this DR. For that purpose, this data register is being used in this configuration, where we are having some more variable over here. One is your stack pointer, full and empty. Now, what is stack pointer? Which is pointing to the top of the stack always. TOS, top of the stack. And in this case, it will be holding 16-bit of address inside it. So stack pointer is a container of address. Address of what? The location of the top of the stack where the data is being stored. So we are having two more flags over here, full and empty. Now, what is the purpose of this full? It will be holding only 1 bit of information in it, either 0 or either 1. Same in case of empty, either 0 or either 1. 0 means the stack is not full right now and it is available for insertion. In that case, we will be performing a lookup operation on a full, we can say, flag. And the value 1 means, if the value of full 1 means, it means there no further insertion operation can be done if the value of full equals to 1. If the stack is full, we cannot insert any new element to the stack. In case of empty, if empty is 0, it means we cannot perform any deletion operation on a stack, as there is nothing to delete from the stack when the value of empty is 0. In the deletion case, we perform the lookup for the empty, we can say, flag. And if it is 1 means it will be containing some data and we can go for your deletion operation. That is your pop operation. Push in a case of insertion operation and pop in a case of deletion operation from the stack. And LIFO means the element which is last to be in will always be first to be out in a deletion operation. For pushing, we will be pushing to the top of the stack and popping from the top of the stack as well. So this is the kind of, we can say, the stack organization in a register. Here, we are having certain instruction written over here for pushing and popping operation, pushing for insertion and popping for deletion. In push operation, what we are doing first, we are incrementing the stack pointer. Now, let us have a look how we are incrementing. Now, before inserting a new element to location number 4, what we need to do? We first need to change the location where we want to insert the data. For doing so, we need to increment our stack pointer. That's why, if right now it is locating at 3, what we need to do? We need to add 1 in it to get it to location number 4. So here, the first operation is stack pointer need to be incremented. SP equals to SP plus 1. And after that, when it is incremented and it will be pointing towards this our empty location, we need to transfer the data from where we are getting the data, which is already stored in data register. So what we will going to do, we will be copying the data from data register to memory stack pointer. M of SP means the memory content which will be pointed by our stack pointer, this location. It means that M of SP, and here we are inserting our data, and data is now being pushed into your this stack. After that, we will be looking for this condition, that is after insertion, whether the stack pointer is 0 or not, whether it is going to some 0 location. If it is so, then this operation will not be possible. Then you have to change this also. If SP is equals to 0, then full equals to 1 means there is no place to push the new operation. To check those conditions, we are checking this. And empty equals to 0 means popping is possible, but in pushing is not possible after implementation of this state. So before executing the next pushing operation, we need to clarify this if statement. Okay. Initially, we have to go for this statement also. Whether empty is 1 or full is 0. We have to look for the insertion as well as deletion operation, pushing and popping. Same with the popping. In popping operation, what we are doing? The opposite of this operation. What is the opposite of this operation? Now, we need to remove this C from here and want to copy it to DR register. So, what we supposed to do? First of all, the stack pointer is pointing toward the C. Okay. So, how it is possible? It is pointing. I cannot move this pointer immediately to the next location before popping that element. So, for the very first step is to remove that element from the memory and copy it into the data register. So, what we are doing? We are removing C and storing C in your DR. And after this, we will be updating our stack pointer to this location. So, for doing so, what we need to do on these addresses? We have to decrement it. So, 3 minus 1 is 2. That's why stack pointer is becoming, first copy the data, okay, then decrement the pointer. SP equals to SP minus 1 by 1 value. We cannot jump to 2 or 3 values in stack. We can only increment it by 1 or decrement it by 1 because we need to remove or insert an item to the top of the stack. That will be done by only one incrementation or one decrementation. We cannot go for plus 2, plus 3 and all. Okay, so this will be decremented and now it will be pointing to, after deletion, it will be pointing to the top of the stack. That will be containing the operand B. And after that, this condition is being checked. What need to be checked? SP equals to 0, then empty. If empty is 1, it means nothing. We cannot perform the pop operation beyond this. If empty is 1 means the stack is totally empty. We cannot pop any element because the element is not lie in your stack. So if it is positive, then the pop operation, next pop operation cannot be done on the stack. Full 0 means nothing is in your stack. The vice versa. So these two flags are opposite of each other. Now next is your memory stack organization scheme. In the memory stack organization, as we have looked, again we are organizing this memory in a form of a stack, but some reserved portion of memory, not the complete memory. Here we are having program and instructions as well. Along with your stack pointer, we are having address and program counter also over here. Okay, so they are working with this program instruction and data. Address is pointing towards the data already being stored and program counter. So here the major point to have look at it is the addresses lie in opposite order as it is in the previous one. Here we are using ascending order. If I am starting from lowest to top, and here we are using descending order. We can say 1000 is there ascending in this and descending in this order. So here the operation for push is totally changed. It will be now SP minus 1 and pop it will be SP plus 1. Why to do so? Because it will totally depend upon your addresses number. If I want to remove an element from the top of the stack, I need to to increment this 3000 to 3001. Then the cursor is going to be moved. That stack pointer is going to be moved on this location. So I need to increment for popping operation. That's why it is opposite of this register organization. So though both the operations are, so we cannot fix the addition or we can say subtraction of stack pointer on the basis of incrementation and decrementation. So that totally based upon the addresses assigned to our register or to our memory. On their order, it will be the dependency of these operations. Okay. So in this, the same operation is being performed. For pushing, we will be decrementing the value because I want to insert. So I need 2999 over here. Okay. And for this popping operation, we will be need to increment the stack. So most of the computer do not provide hardware to check the stack overflow and full end. So that's why we are having this. So we need a software in case of memory stack organization scheme to know about the stack overflow and underflow. Whereas in register, we are using these flags. The flags are also a kind of, we can say, which will be holding one bit of data in it. Here we are not using flags. We are just depending upon some software to know whether your stack is underflow and overflow. So that is all about my presentation for the today. Hope you all like it and have this connection for this. You're getting all these points easily. Thank you and Jai Hind to all.